Hi, my name is Shahnawaz. In this lecture, we will study the polynomial functions and polynomial maps. We know that the best way to study the spaces with a structure is usually to look at the maps between them that preserve the structure of the space. So likewise, we want to study the maps between the affine or projective varieties that are compatible with the structure of the variety. As algebraic varieties are zero sets of polynomials, so one should expect that the functions are just polynomial functions. Now to define these functions, let us first define the coordinate ring. So we have this definition. So let X be an affine algebraic set, and let Ix be the ideal of X. I mean the set of all polynomials in the polynomial ring in n variables x1 up to xn that vanish at x. I mean the restriction map on x is actually the zero map. I mean f vanishes everywhere on x. So this is the vanishing ideal of x. So this is be the ideal of x. So then the affine coordinate ring. So then the coordinate ring of x is defined as so it is defined as the quotient of the polynomial ring modulo the ideal of x. So one can note here the coset of a polynomial. So the coset of a polynomial, say capital F, in the polynomial ring in AX. So this is denoted by the F with the square brackets. So this is the equivalence class of the polynomial F. So one can note over here that this this ring AX is actually the integral domain only if Ix is a prime ideal, but Ix is prime if X is a closed subvariety. I mean if X is irreducible. So let us make a remark here. So if X is irreducible, then we know that the ideal of X is a prime ideal. And hence the coordinate ring AX is an integral domain. So actually this coordinate ring, I mean this quotient ring AX is actually a K algebra. By K algebra we mean that this ring AX is a ring and contains K as a subring. So note that AX is also a K algebra. Let us do some example. So let us take x to be the zero set of the polynomial. Say uh, let us say it is the zero set of the polynomial y minus x squared, which is a parabola. So obviously this is a subset of the affine 2 space. So then ax is actually the polynomial ring xy modulo the ideal of the zero set of this uh, element polynomial, which is same as the quotient ring kxy modulo the ideal generated by y minus x squared, and one can see this is isomorphic to ky. So we can either view ax as a ring or a set of functions on x, namely the set of all functions from x to k which are given by uh, polynomials. So let us define these polynomial functions. So let us consider x to be a subset. I mean, let us suppose this x is an affine variety, be a closed subvariety, be a closed subvariety. A polynomial function uh, say little f is a function from x to the underlying field, which is k. So a polynomial function f from x to k on x is actually, and the restriction map is the restriction f restricted on x of a polynomial f of a polynomial f in the polynomial ring in n variables. Uh, that is same as to say that the little f of p is same as f of p for all points p in x. So then we call this little f a polynomial function. So we also remark here that the set of all functions from, so the set of all polynomial functions from a k algebra, so these form a k algebra, form a k algebra under pointwise addition and multiplication. That is, if we take two functions f and g, then f plus g of p is same as f of p plus g of p and f times g of p is same as f of p times g of p. So under these operations, this is a K algebra. So here after we will always identify the coordinate ring AX with the set of so let us write this down here. So we always identify the coordinate ring AX with the set of polynomial functions. So so actually this follows from the fact. So before proving this, I mean before saying this, we have a result here in proposition. So the proposition says that there is a K algebra isomorphism between the coordinate ring AX and the set of all polynomial functions. So there is a K algebra isomorphism between AX and the set of all polynomial functions on X. So that is, so let us prove this. So define a map say psi from a polynomial ring kx1 through xn to the set of all polynomial functions. Set of all polynomial functions in X. So we define this map by, so psi takes the polynomial f to the polynomial function. I mean f restricted over x. So then clearly psi is a homomorphism of K algebras. So clearly psi is a homomorphism of K algebras. This psi is also subjective by definition because we have defined the polynomial functions precisely as the restriction of polynomials. So psi is also subjective uh, since we have defined polynomial functions precisely as the restriction of polynomials. So now to exhibit the kernel of psi, so also if we look at the kernel of psi, it is the set of all polynomials in the polynomial ring in n variables such that the restriction of f over x is 0. I mean f vanishes everywhere on x. So which is same as the ideal of x, the vanishing ideal of x. So hence by first isomorphism theorem, if I look at I mean the so it follows that if I look at ax, which is by definition the quotient of the polynomial ring x1 through xn modulo the ideal of x, which is the kernel. So this is isomorphic to the set of all polynomial functions on x. So that is why we always identify the coordinate ring ax with a set of all these functions, polynomial functions. Now we have a remark here. So two polynomials f and g define the same polynomial function over x if and only if their difference is in the ideal. So two polynomials, say f and g, in the polynomial ring, so they always define the same polynomial function if and only if their difference is in the difference f minus g is in the ideal of x. So let us prove this. So suppose the difference of the polynomials is in the ideal of x for some f and g in the polynomial ring. That means this polynomial, this vanishes everywhere on x. So therefore if I look at the difference of f and g, then the restriction of this polynomial over x is 0, or f minus g of a point p is 0 for all p in x. This is same as to say that, so that is f of p is same as g of p for all p in x. This implies that if I restrict f over x, this is same as the restriction of g over x, because f and g they agree on x. So that means these two functions are same. So f and g they exhibit same polynomial functions if I assume their differences in the ideal of x. So conversely, suppose the polynomial functions are same, so then the difference of f and g rest over x, um, this is 0 everywhere, or the difference of these two polynomials is in the ideal of x. Now we proceed to define the uh, these maps. I mean, so here Fn is using the ideal of X. Now we have a definition. So let us consider two algebraic sets. So let X be a subset of An and Y a subset of A and B2 be affine algebraic sets. So then a map of the form. So we have a map of the form F1 through Fm from the set X to Y, defined as this map takes a point P in X. Let us suppose this point is equal, say this is equal to A1 through An. So it takes this point to the point F1 of P up to Fm of P. So one can note that this point P lies in Am. So this is true for all the points P in X where these Fi's, they are the elements of the polynomial ring in n variables, uh, where I is equal to 1 up to n. So a bijective polynomial map whose inverse is also a so let us write this down here. So a bijective polynomial map whose inverse is also a polynomial map. Whose inverse is also a polynomial map is called an isomorphism. So is called an isomorphism. So if this map turns out to be a bijective polynomial map whose inverse is also of same kind, then we say X and Y, they are isomorphic algebraic sets. So one should note here in this map depends only on the polynomial functions. So note, so the map P, which is this map over here, F1 up to Fm, depends only on the restriction of these polynomials over X. So F1 restricted over X up to Fm restricted over X, because we restrict, I mean we give inputs to these polynomials from the set X here. So that is why this map phi depends on this and these restrictions, which are the polynomial of functions. So thus phi is also defined. And thus phi is also defined by m tuple of polynomial functions, because these are polynomial functions, m tuple of polynomial functions. Now let us do some examples of these polynomial functions. So the first example is, let us take x to be equal to the affine 2 space and y to be the affine 1 space. So then the projection, then the projection. So if I take the projection map x from A2 to A1 given by, so it takes this point, this x takes the point A B in the affine 2 space to the point A. So all this space is mapped to this line over here. So this is an example of a polynomial map. So this is a polynomial map. So let us define one more example here. So now take x to be the affine 1 space and y to be the zero set of the polynomial y minus x square, which is of course a subset of the affine 2 space. So then the map, say t square, which takes this map is from the set x to the set y. And so this is given as t square. So it takes a point A to a square. Now this map makes sense if this point over here, this lies in the zero set of the polynomial of this polynomial. If a square is a zero of this polynomial, so if we let a to be if we put x here to be equal to a and y to be equal to a square, then a square minus a square is equal to 0. So this is actually a parabola. So this is the zero set of this element here. So this is the point a and this is the set y. So then clearly this point, which is a square, this lies in the zero set of the polynomial. This polynomial. So one can see over here this map is a polynomial map because it is given by a polynomial. So this is a polynomial map. Now what is not a polynomial map? If we define, let us make this a third example. So take x to be the affine 1 space and y to be the vanishing set of the polynomial, say y minus x cube, which is a subset of affine 2 space. So then the map t, say t square from set x to y. So this is not a polynomial map because it is not a map at the first place. So this is not a polynomial map. Since this is not a map at the first place because it does not define a map, because if I take any point over here, so if I take a point A here, it goes to a square, and this a square, this does not belong to the zero set of y minus x cube, because if we let uh, x to be equal to a, then we have here, I mean y to be equal to a square, then we have over here a square minus a cube, and that is not zero unless a is zero. So this, I mean, this is not the case here, so this is not a polynomial map. Now there are maps which are bijective, but even though they ceases to be the isomorphisms. For example, let us define a polynomial map which is bijective but not an isomorphism. So take x to be equal to the affine 1 space and y to be the zero set of the polynomial y square minus x cube. So then the map, now we define this map to be equal to t square t cube from the set x to y, given as this t square t cube takes the point A in the one-dimensional affine space. So note here, this is a subset of the affine 2 space, I mean the two-dimensional affine space. So this A goes to a square a cube. So one can note over here this element, this point over here, this lies in the zero set of the polynomial y square minus x cube, because if we let uh, x to be equal to a square, then we get x to the power a to the power 6 here, and if we let y to be equal to a cube, then we get a power 6 also here. So we have a power 6 minus a power 6 is 0. So of course this point over here, this lies in the zeros of this polynomial equation. So this is a polynomial map. So this is inside y. So clearly, let us call this phi over here. So clearly phi is a polynomial map. It is also bijective. So this map is bijective, the inverse. So this map is bijective with the inverse. So this inverse is a map from y to x. So we have to give some input here, and we wish to get I mean a one tuple here over here. So what we do, we define this map. So we define it as, so we take phi inverse at point a b. So this a b, this is of the form, so since this point a b is in the set y, which is the zero set of the element, I mean zero set of the polynomial y square minus x cube. So this point is of the form t square t cube. So now this element comes from when we I mean when we give t as an input in the map phi. So Now from this point A, we want to get back the point T. Now to get back the point T, what one has to do, we have to take T cube and we have to divide it by T square. So this map is actually given as, so this is equal to B by A if A is not equal to 0, because when we divide the second coordinate by first coordinate, then we get back the point T, and when the first coordinate is 0, the second coordinate is 0 as well. So phi inverse 0 will be 0. So it is 0 when the first coordinate is 0. So this is the inverse of this map. So this map is bijective, but this phi inverse is not isomorphism, because phi inverse is not a polynomial map, because it is not given by a polynomial. So that means bijective maps, polynomial maps also, they may cease to be the isomorphisms. So if we look at the graph of y square minus x cube, so it is like this, and so this set over here, which is the input, which is a1, the same as x, and this input over here, which is y, the same as 0 set of the polynomial y square minus x cube. So these two sets, they are not isomorphic, even though they are homeomorphic. So there is something with this point over here. So this point, in some sense, is not like this point over here. So these two maps, these two sets, they are not isomorphic, although they are homeomorphic. So, but this map, I mean phi inverse, is not an isomorphism. Since the map phi inverse is not given by a polynomial. Since phi inverse is not given by a polynomial. Now let us define the pullback of a polynomial. So we have a definition. So let X be an affine algebraic set and Y be a subset of AM, which is the affine algebraic sets. So let P be the map F1 up to Fm from X to Y. So this is given to be a polynomial map. So the pullback, this is a polynomial map where these Fi's, so where Fi, they are in the polynomial ring in n variables for all I is equal to 1 up to n. Now the pullback is actually a map, say phi upper star, from the coordinate ring over y to coordinate ring over x. So this is defined by phi star takes a polynomial function, because we can identify ay with the set of polynomial functions. Similarly, we can identify with ax with the set of polynomial function. So it takes the element h and is given like this. So it is h composed with phi. So one can note over here. So note that uh, for point, say if we choose a point P which is called a1 up to an inside X, and if h is a polynomial function which is same as the polynomial h restricted on y, where h is in the polynomial ring k x1 up to xn, and then we have, if we look at phi star of h operated on the point P, so this is same as h of phi of P. So this is same as h of phi of P, which is same as h of f1p up to fmp. So thus phi star h is same as h of f1 up to fm, where h, where this expression, I mean h of f1 up to fm is a polynomial in x1 up to xn by replacing by replacing uh, y, by replacing in h each yi by fi. So where this is a polynomial in x1 up to xn by replacing in h each yi by uh, fi x1 up to xn. Now one can determine a polynomial function by these pullbacks. So, but before that, one can note that phi star from ay to ax is a k-algebra homomorphism. Now we have a theorem that actually says that the pullbacks determine the polynomial functions. So this theorem goes like this. So let x, which is a subset of an, and y, which is a subset of am, be affine algebraic sets. So the map from the set of polynomial functions say phi from x to y to the set of k algebra homomorphisms. So k algebra. So one should note here that this phi star from ay to ax is a k algebra homomorphism. So this is a map. I mean, the map from this set to the set of K algebra homomorphisms from AY to AX. Let's call this phi star, which is given by this phi goes to this phi goes to phi star. So this is a bijection. So there is a one-to-one correspondence between the polynomial functions and their pullbacks. So this is a one-to-one correspondence.